works in nuclear power and atomic energy, which has a branch that works on telecom and IoT of about 400 researchers. So it's quite a critical mass anyway. The company itself is about 15,000 people, researchers. That's quite a big deal. So the title of the presentation is IoT and 5G, opportunities and challenges. I guess during these days you have been listening to many aspects of IoT. I don't know how much was covered on the domain of the telecommunication part itself. So we'll see it together. So you have listened probably to many definition of the IoT. Here you have prepared some that make sense for what we want to discuss here. So we want to put focus actually on the need of specific communication infrastructure to deliver service that we can have with IoT. So the first definition is on a dynamic global network infrastructure of adaptable and interoperable devices integrated in a common information and communication network. So the important thing that actually, for some people working in IoT, what they really see is the dynamic part, and you have to adapt, and you have to have interoperable relation between different devices. Then another definition that can work to focus on what we want to discuss is actually there's a collection of technologies, so that sounds like heterogeneity indeed, that make it possible to connect things like sensors and actuators in the internet, whereby allowing the physical world to access to the software. So this is also that drives the concept of the cyber-physical system, for which I guess you are familiar with. So the idea that actually we have the physical sensors, but we have also logical usage of this sensor, for which we can make it work together in different way, in a very modular way. Then there's a layer of digital connectivity on existing infrastructure and things. This is the idea as well that you can make evolve the structure we have, including intelligence, make it smart with the sensors, and then again you can have this artificial system that does things that deliver service that they were not for before. A vision on employing the network devices and application in business information signal processes. Here start introducing the concept of also of the social impact of IoT, and we will discuss it more about. Then there is the definition, let's say, from classical definition from the European Commission, where actually wants everything in so they interconnecting anything, anytime, anyone, in any place, any service, and any network. That's clear that actually there's no global with this. There's a classical definition where we don't know what we're speaking about, because actually say just does everything. A world where the real, the digital, and the virtual are converging to create smart environments to make energy, transport, cities, and many other more intelligent services. So here again is the idea that actually IoT is one of the elements of the cyber-physical system, and one of the other elements also the communication part. What is definitely a reality today that actually devices is there. Well, we have been working in the last 10-15 years about really how to interest devices, how to have energy harvesting for devices, how to have good batteries, good communication modules for the sensor itself. Now we have on the size and of engineering level for which the biggest step on the device itself is done. So the problem is not more on the device, how you network devices, how you exploit devices. So we have been spreading the last 15 years sensors almost everywhere, and actually creating smart environments in application, like for example what they call the smart plants, where we have environmental sensors for the water, leak and quality, pollution, weather monitoring, and so on. The context of smart cities, on which you can have, I guess, an extended presentation later, but where actually you put different intelligence with sensors in a city in order to to control the traffic, to steer traffic lights, to monitor the hair solution, to check the security of people, the camera, and so on. So all the things. The smart energy with energy grids, where actually you have sensor and actuators for which you plan how to distribute the energy in a very short-term manner, according to where is the demand, where is the offer, and where also there are some collectors that move around the city, around the place, or the grid, that can bring energy from one place to another. Think about, for example, electric vehicles, which has batteries that are thought also to be like an element of transfer energy in a place where there's not enough energy. Then you have smart buildings, where you put sensors, for example, in the infrastructure of the building to monitor the health of the building, where you control the environment inside the building, like for example the air quality and other things and so on. Smart transport, it's quite a fancy point at the moment, because we're thinking about, for example, the autonomous driving, which actually is a nightmare, because it means you need to sense some measure, you need to communicate in very fast manner. When I say very fast manner, less than 1 millisecond, and then you need to actuate. For example, things that you detect a car is coming, you have to send this information to a control unit, and then start the brakes and so on. So those are, from the technological point of view, very, very complicated point. And again, the sensor itself is just a part of this. The point is how you control, how you figure sensor and communicate. Then there is also the smart industry, or what people call industry 4.0 or factory of the future, where actually the point is that you put sensor in the industry chain, so in the production chain and so on, and you want to have a fabric where you can do different things, because actually, because you have sensors to detect what you're doing, how you're doing, the rhythm you're doing, the kind of material you're doing, you can have more multiple industry, and then you can do different processes with the same infrastructure. Smart health, that has been maybe one of the first, was one of the first application in sensors, also the one that had more success at the beginning. So we monitor people, the biological measure and so on, where you can have remote health control and so on. But now what is changing is that now we use this data as well for estimating the stress of the people, how they're enjoying the given context and so on. So actually we are starting going into the pervasive part of this, where actually we are collecting data with our IoT. So again, the sensor is just the unit sensing, but what we do after that, so the data mining, taking the data and so on, and doing some other decision somewhere else. And then there is a smart living. Well, okay, it's more on entertainment. For example, when you go to the cinema, you sit down and depending on the kind of movie, the lights are different. So this kind of things are more, say, small. Then, so we have a different connectivity area now. So now things are connected to things, either without a human in between. So we have people that are connecting to things. So, for example, what you have with your smartphones or your some kind of wearable devices, where you recreate it, monitor all the time, you measure how many calories you use per day and so on. And all this data actually is used for other things. Actually, it's the profiling people. And then you have connection of communities. Let's say, for example, we might have a connection here as attendees at school, for which we can monitor, for example, how you enjoy the event and so on. Or it can be at a city level, or a fleet of workers in the same company and so on. So there with people there tend to console, whatever. So the idea is actually there is a social aspect of the IoT, which actually is exploited to gather information or circle different people. Yeah. So all this creates actually new opportunities for the internet, bringing to the internet everything. So roughly, as far as I have sensors, as far as you're able to communicate, putting communication between them with a good constraint in terms of latency, availability, and so on, then you can create your own service just with some software to control that. If you see the technology roadmap of IoT, actually the evolution, it's it's quite interesting because at the beginning we're indeed just going on the sensor itself and trying to do a specific measure that were delivered to the sink. Then we had the sink was moving around trying to collect this this information, and then we start this kind of huge amount of federation of sensors going to what we call this vertical market application, which we start having this smart transport, smart energy, and so on. And then now we are today facing the area of the ubiquitous positioning and going to have this real world web where actually we can have a completely virtual representation of the world, which actually has a physical measurement of what you have, but you can decide exactly what you extrapolate from that. And if you look what can be done with the first generation of cellular network, the 4G, I hope you are familiar with. If you take your telephone, sometimes you have this 3G or 4G, that's the generation of telecom infrastructure you're using. And actually, the 4G, actually, the capability of the network is actually able to answer to some specific requirement that goes to the actually to few units federate together. So the requirements up to the service delivered in 2010 were enough. But now, if you go to which is the real target, so ubiquitous positioning and have real world web for which interaction is very fast and so on, requirements of 4G are not enough, and we need a new generation of telecom. That's the reason because IoT needs 5G. Then I will give some numbers later. So the reason because 5G needs IoT is different. So there's a kind of win-win context. Because, so IoT needs 5G because actually it needs better connectivity, better reliability, and we'll see the details for which you can meet all the stringent requirements you have in the new application to the market. But at the same time, the problem with the mobile market, classical one, is actually at the beginning 2G, we were selling voice. So you were paying quite a lot of money just to communicate with people. Then arrived the data, and then people already were selling the data as a contract. But now what's happened that almost everyone can pass through the data, and the voice itself is not giving any revenue. And then if you see what you have to, the data you have to provide to the user to have a given revenue is very low. So actually, the market of IoT is demanding somehow still a low data rate. You can see in this graph. But the point is not shown here in this graph is how much money you can do for bit of data rate you're delivering. The added value of the service, the IoT is much important. That's the reason because a new generation is investing on bit shape for IoT. So that's just a view on the classical telco market as it is today. So you have a voice at the beginning was a good revenue source. Then we start with the data, and then when we start with the data, until we got this huge gap between the traffic you have to deliver and the revenue you can have. So that actually imposed to the telecom operators a revolution, and the revolution is to make a telecom system as a network as a service. So you do not deliver anymore the connectivity itself, you deliver the service. And to deliver the service, you need a sensor. You need a link to the physical world. IoT and the real world web are one of the unique opportunities to save the telecom market. Otherwise, there will be not enough revenue for that. So actually, we are indeed creating a new internet of many things. We actually want to optimize, want to adapt, want to secure, advise, control, actuate, and so on in what I call, I said before, the cyber physical systems, where you have indeed the physical world to the left. You are in the physical world, sensors are placed there, and then you have some measurements on. Then you have an IoT system where actually make a virtual representation of that, just selecting few parts that are of interest, federating that together, and then you have the service level where actually you are requiring of interacting with a specific part of the physical world at a specific time. So this actually enables different new internet. One of the internet is the internet of energy, for example. New, I mean, it's still 5 years now. We start with that. We're actually you treat energy as a packet of information, and you deliver or you route this energy in a location where you have interest in. Then you have the internet vehicles or the transport system, where actually you monitor, control, and decide where to route vehicles, people they are traveling, and so on. And that is again is thanks to the thing that you can do specific measurements in a place with a sensor, but you're also able to communicate in a given time frame or with a given reliability on doing that information, and then you can actuate. For example, you can trigger a traffic light to be red, and then you stop and so on. Then there is also what they call the internet of water, where actually what you do, you have there are two major problems with the water management. First of all, is the leakage detection. You might have a leakage, and then you lose all the water, and you don't know for a month. So first point is really using the smart sensor, having smart pipes. You control the pressure and so on. You can detect if there are any leakages. But the second problem is actually you have an offer and demand, as in many other systems that change by time, and actually how you can manage to match offer of water and demand of water. The thing that we are speaking about water, normally speaking about we are talking with plumbers, so people that really, I would say, have a very basic view about what can be done in a short time. So we are revolutionizing actually the market here, because we are introducing intelligence for which we can really control in few seconds actually where there is a need to combine water one sense and another. Somehow the abstraction is the same. So again, you have physical world where you put sensors, you have a model of what exactly you want to control, and then you have a software that actually drive you to the good actuation in a specific. Then there's also the case of smart cities, which is an excellent use case with a mixture of everything in it, because you have a smart transport, smart water, smart quality air monitoring, smart lighting, smart. And actually, you have to put all the things together. Here, you have a problem that's not solved yet, which is actually the interoperability between different standards. I don't know which part of the IoT have you been working or studying on, but normally when you work with the IoT, from the communication point of view, you think about a one-hop, two-hop communication. That means actually it's local communication. So you can have a specific standard for your sensor that communicate together, you don't care about the rest. Now the problem here is that actually you have many sensors operating on the same physical area with different standards, so they do not understand each other. And if you want to do, for example, measurement, if you want to do weather prediction, so you need the humidity, the temperature, the pressure, and so on, and you need that those sensors speak together, and that is a challenge there. So you have so an example what you can have, for example, I will go quite fast here, but just to show you the heterogeneity of the point. So in smart cities you have different applications like the smart parking, the structural health, the noise urban maps, traffic congestion, waste management, intelligence perceiving system, and so on. So you have different applications with different requirements. So when you have the telecom system have to deal with that, the question is how can be flexible enough to meet all the time this requirement. The environmental as well, you have forest detection, or pollution, earthquake detection, and so on. And still, you have different characteristics. Just to give an example, if you have the forest fire protection, maybe you monitor the fire presence every hour, or half an hour. If you are doing a smart transport system, you're monitoring if there is no collision every millisecond. So the question is how you can use the same infrastructure to convert this information. And then, as I said before, with the quality, with the language, and so on. in smart grids, there are also different applications that, for example, as well, the monitoring of the performance of solar energy plants, because depending on the time and the specific day, you can produce more or less energy, so more or less energy you can inject in the grid, and so on. So you have the retail, the logistics, industrial control, agriculture, animal farming, and so on, health. So, but all these different applications have different research challenges. For example, in the case of smart cities, one of the major research challenges is the cost-effective deployment. The problem that first approach was, we have sensors, a lot of sensors, I want to sell the sensors, so we deploy sensors. But then the point is how smart you can deploy that. First of all, you don't want to deploy too many, and then because actually if you create an overcrowded solution, overcrowded context, then you can know how to deal with all these sensors, also how to deal with the maintenance of the sensor. So you need a network that allows you to federate sensor in a smart way, in a long range enough way for which you need less sensors in the physical system. You have also, again, the problem of the scalability. Let's say you engineer a system for work for 100 people, but then you want that it works for 1 million people. And then actually the question is, do you have to think my system again, or can it be scalable enough? This is one of the major problems in the today IoT, because we will see later, really scaling up a lot. We are thinking about having between 300,000 and 1 million of sensor per square meter in the next future. Square kilometer in the next future. That means like really, today it's maybe some tens, some tens, maybe 100, whatever. So the problem is that really how you scale the system, and one point is how you scale the communication part, because otherwise you can have interference in communication and so on. So it's quite complicated. The other point that's one example is a smart energy is when you have actuators, you need to have real-time communication. That means actually you measure something and you need this. I mean, it's an engineering approach. Normally what we do in engineering, we do a measurement, we estimate a value, and then we say, okay, this value will be good for the future, so we do the prediction. What's up? That actually, if you look at the current time of your measurement, okay, the current time, so the period of time for which this measurement is valid, should be long enough that you use this measurement before. So if your communication system has enabled you to communicate and to actuate in a period of time that is short enough for which you measure is still valid, then you can use it. Otherwise, you do what we call misadaptation, and you do something catastrophic. For example, you want to switch, you want to put the green light, and then actually at that time it's better to put the red light, and then you have an accident. So it's very important that actually your system, and this is one of the major challenges, goes to end-to-end delay. That's quite sure to give numbers, 10 milliseconds sometimes. And the classical application we started with IoT was thinking about hours or days. So it's now with the new service we provide, this is a critical part. And this is one of the major challenges that are not covered in 3G and 4G networks. And actually, we're trying to cover in 5G. Then other problems in smart transport and mobility is also the incorporation of the human in the loop, and that means actually again we have a physical system, and they have this remote control, and the people can interact with this, not necessarily being physical there. So actually again this is the problem of connectivity. You need to be connected to the data, and also delay. And both things are quite complicated, because most of the time critical action today are still with wire connection, because wires is not good enough. I don't know if you are familiar with what we call deterministic process. So what is a deterministic process? Roughly it's that actually, like in a factory diffuser or factory process, you have a supply chain, or you have a production chain, sorry, and then you have action A, action B, action C, action D, and so on, and everything goes in a specific logic. It's deterministic, no randomness. So what you do, you scramble, or whatever you do you engineer, and then you find the optimal process. So to do that, that means actually that action A finish before action B start. Then action B finish before action C start. So that means you might accept some randomness in A as far as you're sure that whatever is the randomness, that's over before it's needed by action B. So now we understand why the delay is that important. Because actually, if you do the measurement and you want to transmit it with wireless, now with wired you know exactly the delay. Yeah? You have some randomness, but it's really negligible. But with wireless, first of all, you're not sure to be connected. So first thing, you might never deliver to B. Second point, you might deliver too late. Too late means roughly not delivering anyway. So, because actually it's too late for the action on one, and you block the optimization on the chain. So it's important, very important, if you want to apply, if you want to enhance processes that today are deterministic with stochastic tools like wireless communication, then you need to be sure that some of the limits, some of the constraints you have in your wireless system are good enough in order that the process feel what's happening as deterministic. I don't know if it's clear.
Isn't this something that we already have in 3G and 4G?
No, we don't. It depends on the process. For example, fire detection. Yeah, we have. If you are measuring every hour, okay, that's fine, because you have an end-to-end delay in 3G or 4G that might be, I don't know, in reality, maybe other seconds, so it's okay. But what you don't have, maybe, is that if there's fire and the sensor is down, you're not delivering information. Okay? So you don't have enough redundancy, maybe, or resilience in the system. Okay? But if you have to, for example, to do the autonomous driving, okay, you have the Google car.
Yeah.
1 second, in many people having an accident in a day. Okay, yeah. So you need to have this end-to-end delay in communication that's on the order of millisecond. We don't have that, not at all.
Yeah, that's about the part of the response time that 5G can improve.
Yeah,
what you have now, but how? I don't understand the mechanism to know if it's connected, because you're talking about wireless. We will be able to do deterministic software. If there is no connection, it's the same for every protocol.
Yeah, thanks for guys. So it's how to say connection. Let's say that you have a basic communication system for which the only way to speak to each other is to be face to face.
Yes.
The only way. All the other angles are not possible. Okay. So if you use the system, there's only one way, face to face. So most of the time, we do not have connection. If you improve your system, and you can be in any angle, and you have a good enough connectivity, then you solve the problem. What we have today in 3G and 4G, in many cases, given the positioning, the scattering, the physical medium used for communication is blocked. Okay? And what we are investigating in 5G, how to enhance the system in order to have much less cases, with much less cases where this can happen. Okay, that's the point. So and that goes with usage of different communication techniques, different frequencies, different technologies, and so on.
You're saying that 5G connection could be actually as good as a wired connection?
Yeah, this is almost the target. Yeah. It's I will give the number, but the reliability will be 99.99949 after the point. So operators are delivering the connectivity, so it's kind of really dominating things. And vendors are engineering and producing the units, the base stations and so on of the operators. So all the business today seems to be the downlink, but with the numbers we foresee in a number of senses, the real market will be the uplink, because the real market will be the users and the unit that will try to connect to the network. Yeah. So the end-to-end delay, which is in 3G and 4G, is too long and not predictable. There's another point. You still, even if it's too long, you can downscale your system somehow. Let's say, for example, you are in an area where your Google car is not enough connectivity and so on. You know that, and you switch to manual. But if you cannot predict, that's a big problem. Because like, if you do not switch to manual, then you're down again. The localized computing was saying before, you bring some of the computation, all the computation to the cloud, and then there's a problem today that actually, if you want to bring to the cloud, you need a backhaul and fronthaul. So you need to send somewhere all this huge capacity of data. Things. I'll give an example of you have your telephone, you want to do virus scanning. Okay, virus scanning, it's quite a nightmare because you need to, if you do it on your telephone, it takes a lot of time. But if you want to do somewhere else, you need to transfer a lot of data, compute very fast, and bring back to you. So if the communication system is good enough to send all this data in a very quick manner, it's valid to do. Otherwise, you prefer to do it in device. So this kind of thing. We're going to face extreme density of IoT devices, which is now it's not supported. So again, 3G and 4G have been designed for mobile terminals. And when in a base station you cover, let's say 1,000, 10,000 users, it's already a big number. And you have several square meters of coverage with this kind of a station. We're thinking about several millions of units on this entire area. So the system is just not engineered for that. So it's just not possible. And one of the reasons is also the communication of it, because today, what you do, if you want to send, for example, information about a sensor saying, I'm alive, that's all. Okay, just I'm alive. Then roughly you have to use a packet, a telecom packet. This telecom packet normally is made to deliver 15,000 bits. You just need to send 1 bit. So the overhead cost is very costly, and then energy and so on, whatever. But so there are some solutions on what they call, but actually they call it different way, but it's nothing more than a piggybacking. Are you familiar with the concept? So you have a packet you send for some reason, and you just put on the back of the packet another information you want to deliver to this, and then we call carrier grade. They have a very fancy name, but the concept is very old. It's piggybacking. But still, with this piggybacking, you need to send address with sending, and so on. And the overhead still is not very good. And there, you can really have a factor of maybe 1,000 on improvement on that domain. And this is something that's starting now. And what is very worth to see, people that do this kind of research with the density awareness of sensors. It means actually in some area, you have few sensors, so you don't care much. You don't do all this complication. In some other areas, you have a lot of sensors. You have a huge density, which you have to tune this low overhead. If you have any questions, just stop it, okay? Because I can speak for hours, but maybe if you... Okay, so the IoT weakness today, we need an effective communication network, and we need at least to be availability in the time we want, and the reliability of the network. And either things are evolving that we don't have what we want, and the network is also changing today because we are delivering connectivity anytime, anywhere, and anything. So it means actually we also the edge of the network want to have this target of very high connectivity. So now, what can do for us the 5G? So has anybody of you already heard about some of the details of 5G, or so you are completely first time? You have some news. Okay. So, so the key challenges in 5G is not only IoT. It's first of all the very high data rate. Okay, and that answers to the problems I was saying before of the frontal backhaul. Then there is the problem of Internet of Things, with very large number of devices with very low data rate most of the time. And then there's also the problem of the spectrum. I don't know if you thought about that, but actually when you want to communicate in wireless, you need a spectrum for doing that. Now what's up? Then in IoT, normally you want to have low power devices. Small devices, low power devices. That means actually low power means your transmission power is very low. And a small device means you don't have too many antennas, you don't have too many fancy things so that we can have an base station for a long range. So the spectrum is not equally good. The higher is the frequency, the shorter is the range of communication you can have, in principle. So we try to convey actually sensor communication in a very low band, like say 400 megahertz, 400 to 1 gigahertz. Yeah. I think that in 5G we are considering for normal cellular system 60 gigahertz band, 200 gigahertz band, either the terahertz band with visible light communication. So it's so from one side you're pushing the system very high in frequency to deliver a high capacity, but for the other way, if you're doing this way for the sensors, coverage range will shrink too much. So that's another big issue for which there's a lot of techniques on agile usage of the spectrum for which we try to use as much as we can the low frequencies for sensors now. The low principle of conjugate radio, maybe you are familiar with. Maybe not. Are you? Okay, so 2 words, conjugate radio was that actually basic way say, I have to speak, you listen. So there's no interference, you know. And then, so that means actually, that's my time slot, I'm speaking.
And that in airports, pilot tower communication.
Once again?
In airports, like 30 years ago.
GSM, TDMA.
Yeah, but yeah. So, but what I mean actually, taking the example here, if we're not using conjugate radio, I will speak, and if you speak, just don't listen to you speak, okay? But that conjugate radio is that we have this connection that someone else is speaking, and then we stop for a fraction of a second, and we decide. So now we decide as a human, but no, we decide by engineer who's speaking. So there is a primary speaker, which has a kind of a leading the discussion, then the secondary speaker we might need to use. So when I'm having blanks in my discussion, you raise a question, you speak. No, that's the way. The same way in communication, conjugate radio things. You try to see whether there's all usage of the spectrum and use the spectrum, because it's very inefficient to give to me. Let's say I'm Italian, maybe I'm speaking like a chatterbox box, but if I was like from some other countries, not telling countries, I don't want people to forget, but that I speak like this, you know, and then there's a lot of room for using this at the same time. Yeah, that's the same thing in telecom. If you have a system that's using just the duty cycle usage of the spectrum is very low, then it's very interesting to give the rest to the others. And that can be used as secondary users, like sensor that are not maybe mission critical communication, that one can use in an opportunistic way spectrum. That's the kind of radio.
It's about cognitive radio.
It's kind of radio. Yeah, that's a different name for that. Yeah, there's a nice tutorial paper if you want to read on kind of radio that gives a lot of information. If you want, I can send you the. Yeah, that's maybe it's 20 pages, but you really have a view on all the kind of radio, also for IoT. Okay, now, so which are the 5G challenges? First driver was the traffic volume. Why? Because again, operators and companies have to sell bigger infrastructure, because services, they say, here, Now you want to see the full HD video on the move and so on. You need 1 terabyte and so on. You want to be at the stadium. You want to point your telephone and see, I don't know, how was the rest of the day before the player, whatever it is. So this is the rationale. Actually, what is worth of that part is having a higher data rate also at the edge of the cloud or at the edge of the network. You can empower cloud system. You can have a backhaul and fronthaul for federated for infrastructure and so on. But the real challenge in 5G is the massive growth of connected devices. Connected device doesn't mean only sensors. It's also more evolved devices like the telephone that do direct communication between them. And the thing again, we are sharing the same spectrum. Either the spectrum now with 5G is much larger than what was before, considering 3G and 4G, but still, we have 10,000, maybe 100,000 more devices in the same area, and then that's the deal. We're thinking about 50 billions of devices in 2020. Think that we are, I guess the target in 2020 is about 7.8 billion people in the world. So there's a trick. Devices there is not only human, but it's also on animals, on infrastructure, on machine, and so on. So there's more than 7.8 billion units already to humans, you know. But you have a car, you have a telephone, you have whatever it is, but still, it's a very huge number, and the 3G and 4G is completely not able to deal with that. And then also there's a largety of diversity of use cases. Why? And requirements. Why? Because actually, as I said before, delivering voice or data is not enough now. So we have to deliver service. And a service might be either customized to the person. So if you have 7.8 billion people, in extreme case you have 7.8 even more billion of different use cases and applications. I'm exaggerating now, but so the problem is really how this network can be generic enough and adapted to the specific thing for which you can either optimize a deterministic process to a specific service. And you have, okay, without going so far, millions in real service, different services. Okay, and in 3G and 4G there are 4 services, only 4. Voice, best app for data, near real-time TV, and web browsing. Okay, so 4 before, now we are already, so we completely revolution the system, and this enables you to have all these IoT then create verticals, ad hoc cyber-physical systems. So, as I said before, if you look at the worldwide population and the connected devices, okay, the evolution. In 2003, I don't remember exact numbers, but the numbers there now. Okay, in 2003, I don't know how many it was, 6 billion people, something like that, whatever. And there was just a few devices, you can see. And then in 2012, exactly, there was inversion, so the quality. So it's about 7 billion, something like that. And then you see that in 2020, hopefully population is not growing that much, so it's not an issue. But still, we have a sense we foresee to have 50 billion. So it's a real market for people. And then the scenarios that we are seeing in 5G is what they call the amazing fast. So actually, we can deliver service in very high mobility. Yeah, let's say for the high-speed train. So high mobility is when it exceeds 150, 200 kilometers per hour. They target to serve up to 500 kilometers per hour. That's I'm a little bit concerned. Great service in the crowd. Let's say, for example, you have in a stadium about a soccer match. You have 80,000 people in the same stadium. There's a crowd. They want to deliver service there. Everybody has a list of 50, 100 sensors in here. And then you want, for example, to measure the heartbeat of people, to see if they're excited to the goal, just into another goal, and so on. All these kind of things. And that actually give you problems about how you access to the data, and how you also do this data mining and so on in the dense crowd. Then another scenario is this best experience for you. Then actually you're here, then you move another place, you take the airplane, then you go somewhere. So you move around by services with you. And that actually means this cyber-physical system is following you. Or actually, it's a human-centric cyber-physical system for which you are the system, and then just communication is just adapted to that. Then the super real-time and reliable connection. So the problem is the delay in reliability. And as I said before, the Google Drive, Google Cars as an example. And then to bigger things communicating, then it's the one, it's I would say, labeled to be the one IoT. We're to be IoT is another part as well. But actually the thing that you have simple devices who need coverage, let's say with problem spectrum and so on, and there are a lot, and now you do. So in order to improve for the fourth generation, fifth generation, we have set some targets which are being able to deliver 1,000 more bandwidth for the data, serve a minimum of 10 to 100 more devices in the same area. It's the minimum because in some extreme cases it's much more. Reduce a factor of 5. Now we're thinking about a factor of 10 about the latency and latency, the system for what I said before, and extend a factor of 10 the battery life. So you can have 10 times more time for using your services. Actually, then if you want to see the evolution between so there are different axes here: latency, peak rate, cell age, data rates, spectral efficiency, mobility, energy and cost efficiency, and simultaneous connection. The gray part is what was covered by 4G, just have a visual point. And then what we are asking 5G. Okay, so we are pushing everywhere. And that's mostly because we have so many more devices in the system. So if you want some numbers, you will have here some numbers that actually things about the coverage. We asked about to improve the cell age about 20 Bs. 20 Bs are according to the LTE-M standard for sensors. Yeah, and the minimum target of a device per access node is 300,000. Access node can be a gateway in a home, actually. Yeah? That, of course, is exaggerated for that number, but it can be a base station in your office and so on. So that's just so the migration 5G is just about communication starts and processing. So we migrate to the service part. This is a table. I guess we're gonna have the slides. I guess we're gonna have. So this is a table. We have all the details. But one thing I want to focus that's important for us is that eventually, I don't know who is fan of IPv6 here. Thanks. But eventually, we convince the community to use IPv6. And so to solve, for example, basic problems for multi-op. And hope for security and so on. So now in 5G, eventually we are using the new generation. And then we can have a lot of potential. Well, and then you have all the other details, whether you can read offline. Okay. So which is the timeline of standardization in 5G and how it can link with IoT. So 5G started, normally it takes 10 years of new generation, okay, of research and testing. So we start 5G research in 2013, and actually we foresee to have the first working test bed in 2018, but the real market will be 2020. So that means that if you want to open your startup, or if you're going to do work, and if you want to really deal with this low latency, high density, and so on, the system will support you. Will be for market will be not ready before 2018. And actually, in particular, if you're familiar with 3G TPT, which is the standardization body that's defining the standards for telecom system, several telecom system, there is the release 13, there's one under discussion now, which actually is enhancing the cellular IoT. The previous version of this cellular IoT was called LTE-M. M is for M2M. And you just have some impact about whether discussing on the technology characteristic and on the chip design implication as well, because you have to think that especially in the low cost and low power devices, when you have some serious changing about the functioning, you need to also have a serious change about the hardware itself. It's not only about software. Most of you are probably have the community on the software. So you see the device that has this, then we can just scramble things together. Actually, if you want to efficiently display some function, you need to have implemented in hardware anyway. For example, about security. So to conclude, I guess I'm also the time. Yes. So we have a lot of devices available today. We are facing this new connectivity area where things, people, and communities are connecting to things. The new approaches started in 2010, roughly, of a cyber physical system are enabling the Internet of X. X is smart grid, smart energy, smart water, smart logistic, smart transport, smart city, smart health. Actually, you can use smart somehow, but that's a good point. It's a good opportunity there. Telecom market today is limited in the revenue because actually delivering data and delivering voice is not enough. So there's a huge will of telecom in order to be a network to deliver service, and the service delivered thanks to actuators and sensors they are placed close to the need. For 5G, 5G is the best. For 5G, the best market is the real world web, and to have the real world web, we need a telecom system that accomplishes these targets, as we said before. Yeah. Then another huge challenge is how to make sense out of all this data. So there's this big data analytics. This is something that 5G itself is not solving, but if you do good data analytics, then you can optimize the process, and then IoT can optimize the 5G functioning. So it's helping, one is helping the other. Let's say, for example, if you just check the density of sensors, and then you have a system that, depending on the density of sensors, you ask more or less spectrum for communicating. If you do the big data analytics in the way that you capture the thing that we have, 1,000 people connected, 10 people connected, 1 million connected, and so on, then you can inform the system, enrich the system, and say, okay, try to ask for more spectrum, less spectrum, and so on. Just an example, but to give an idea that actually it's a move, and IoT is also foreseen to improve the functioning of the 5G system. So the IoT application space is very diverse and very heterogeneous. I said before, 3G, 4G were designed only for data and voice, and there were roughly 4 services where we are thinking about 1,000, 10,000, 100,000, millions maybe on different services. It's completely different. So that it's a nightmare. And there is a problem about delivering engineering and hardware infrastructure versus a virtualized one. So you need a flexible system, and the approach we have today is with the open API. So that enable to include some specific sensor you need, regardless of where we were in the scope before. But again, the problem is that has its limitation, because at some moment you can figure out there's not enough, and then you have to re-engineer the hardware. And then the problem, dynamic interoperability and advanced adaptation, where actually have this massive number of heterogeneous IoT solution, protocol and semantic, and how you deal with it. So, industry and service providers that rely on IoT cannot use the today's 3G and 4G network, that's for sure. So we need to improve the reliability, the short delay, the device energy efficiency and energy efficiency of long-distance communication, the security, and the privacy. Please do not think that's just a second part, because people should maybe decide just to block completely usage of the technology. It can be a complete revolution. People take a big blood and so on, and we don't believe anymore, we just stop this, and we go to the Stone Age back in a few years. Then the X also, backhaul and frontal, and the local cloud computing and storage support as well has to be enhanced on what we actually almost don't have in 4G. So we have a 5G and IoT have a very win-win future, where actually network is as a service for real world web, and the 5G deliver the constraint needed to have this new application that will give your business in IoT. So today the hot topic is this universal solution, and 5G is the best candidate. In order to avoid you have all these standards that you have Bluetooth, you have Zigbee, you have whatever, you have all this stuff, but then when you want to cooperate together, it's a nightmare, no? We want to have an overall umbrella that makes this happen together. And I guess this is the end. Well, thanks for your attention. I don't know if you have any questions, but I'm here.